in the textbook, to get to this, to get the results for the derivatives of sine, cos, tan, and all the reciprocal functions, there's all this theory fluff that starts off with nothing to do with calculus. And you're like, why are you talking about this? Why are you talking about circles? Why are you talking about inequalities? Why are you talking about sine and tan and x and how they're related to each other? That's just weird and confusing. And then after like 2 hours of reading, you get to this graph. And all of the pieces they've been working on for sort of like, it's, you know, we've been working on the this payoff for the season finale for like 20 episodes, and now all the pieces come together and you're like, oh, that's why the TARDIS exploded, or whatever it is, okay? So they do that so that you get this aha moment, and so that everything else is in place before this makes sense, okay? I think that's really annoying. I don't like that they do it that way. Because you're like, I came here, I turned up, and I wanted to do this. And you're wasting my time with all this unnecessary fluff. Just tell me how to do it, okay? Now, part of that desire of mine is unreasonable, but I think part of it is reasonable. Like, it really does take a long time to develop. So here's what I'm going to do. I'm just going to start with this guy straight away, okay? Now, in order to get the results for this, we'll be able to see it in a sort of visual way, but I won't be able to prove it rigorously unless I take a few steps back and look at all that theory stuff. So we're going to go from here, see what we can work out, get some results down, and then we'll do all the necessary proof so that at least you're a bit motivated. You're like, why am I proving this stuff? It's like, well, so that you can actually say the things we concluded, like visually, intuitively, that really are true. Okay? So here's y equals sine x. Okay? And I want to go and work out the derivative of this thing. I want to know what its gradient function is like, how it behaves. But I've only drawn 0 to 2 pi. Can anyone tell me why I only need to draw from 0 to 2 pi? Because this graph is periodic. We've been doing this to death recently, haven't we? Right? So if I can tell you about the gradient function of this part of the graph, I can tell you about the gradient function for the entire graph because it just repeats over and over again. So the first thing I'm going to say is sine, right, is periodic. So its derivative is periodic. Okay? Now, that's a really helpful, it might seem like obvious sort of thing to start with, especially for those of you who know the result already, but it sort of is really great for us because it narrows things down a lot when you think about, well, what could this possibly be? What is the derivative? Okay? Now, let's have a look at this graph and see what we can deduce about the derivative just by looking at it. Just by looking at it. Because you actually know a whole bunch of things, especially by graphing this thing, about how it behaves. Okay? So, for instance, for at least 2 of the spots that I've drawn on here from 0 to 2 pi, you can tell me, without any shadow of a doubt, with complete accuracy, what the gradient is. There are 2 very important spots on here. Anyone tell me what they are? They're stationary points, right? So you've got one here and one here. Okay. Now, why are stationary points called stationary points? Stationary with an A, not with an E. What's that about? It's, well, what does the word stationary mean when you say an object is stationary? You mean it's not moving, it's still, it isn't going anywhere, okay? So what they're doing is they're picturing this graph as describing the motion of an object, okay? And at these points of the graph, that object isn't moving, right? For that instant in time, okay? So therefore, what can I say about the derivative, the gradient, at those particular points? It should be 0, right? Okay, so I'll put a little mark there, that's 0, and that's 0. Now, by the way, what are the values for x at those locations, for those stationary points? Pi on 2 and 3 pi on 2. Good, we're getting there. Radians are starting to sink in. Okay. Now, let's keep going. What else do we know about the derivative of this graph? Okay, well, hopefully when you first learn about doing gradient functions, you often might have given a graph, might be like this, might be like a polynomial or something like that, and then say, now draw for me, you don't know what the equation is, but you know what it looks like, draw for me its gradient, okay? And you'd do something like this. You'd say, look at this part of the graph, from 0 to pi on 2, okay? What can you tell me about the gradient, just looking at that part of the graph? It's positive, because the graph is increasing. So I'm going to put plus signs all the way across here to indicate, I'm trying to say to myself, the gradient is positive at these locations. Now, I can make the same argument, and I can say all the way from pi on 2, the stationary point, to the next stationary point, it's going to be negative. It's a decreasing function. Okay? So you're going to get this kind of thing happening. Okay? I should have mentioned as well, we already said that at those stationary points, the derivative is neither positive nor negative, it's 0, right? And then for my last little section there, from 3 pi on 2 till the end of what I've drawn, it's positive again. Okay. Now, that tells us where the gradient function is going to be with regard to the x-axis. It means from 0 to pi on 2, this little domain here, the gradient should be above the x-axis. In the middle, it should be below the x-axis, and so on. You get the idea? So it's periodic, right? And it's alternating up and down. Up and down and up and down. Okay? Now, what kind of up and what kind of down? Where would you say is the steepest point of the graph? You could make a few different selections and it'll all be fine. Anyone want to give a suggestion? At 0, it looks pretty steep, right? And as you progress from 0 to pi on 2, because you're going from positive to 0, you're thinking, okay, the gradient is positive, but then it's decreasing, and eventually it hits 0. Okay? So it's steepest here. Okay, so I'm just going to put a little star there to indicate that, right? It's steepest there, right? There were other places we said that it's steep as well. What other places are there? At pi, right there, when it crosses the axis, and of course by extension, at 2 pi. All right, now, I said it's steepest, okay, but we have more specific language for describing this, okay? I could say it's not just steepest, but at those points, there's a change in concavity. That's actually what steepness and concavity are two connected ideas, right? So being that you can see, look, I'm concave down, and then I'm concave up. Where I change concavity is where those points of steepness are now. We have a special name for those points. What are they called? They're points of inflection, aren't they? So my stars, I've got points of inflection. Okay. Now tell me, hold on a second. When you have a point of inflection, not always, but usually, what does that tell you about the gradient? What does it tell you about the gradient function? If I've got this, and I'm really trying to work out this, but I've worked out something about this. Okay? Because points of inflection are about this guy, right? When you have points of inflection, what does that tell you about how this is behaving, the derivative? It's a bit tricky, isn't it? Because you're going to be like, what am I describing? When this has stationary points, this is 0, right? But when this has stationary points, this is 0, which is the point of inflection that we're talking about, right? So therefore, at these 3 spots, when I draw my gradient function, however it looks, right, the gradient function should have stationary points, okay? It should have stationary points at the stars that I've drawn, okay? And I've got 3 of them, right? Okay, I think we have enough pieces. What would look like? What would this look like? We said that we've got a stationary point lining up with this, okay? Now, at the moment, because I haven't given you any scale or that kind of thing, you sort of have to guess, but later on we're going to explain, this is why you need all this theory stuff, why this stationary point doesn't just happen anywhere, it happens right here at 1, okay? Y equals 1, right? So there's my stationary point, which is why I've drawn it horizontal. What does it do after that? Well, we said it's got to be positive, but it's got to come down to 0. Positive, but come down to 0. Okay? So it's going to cut through like that. Okay? And there's my stationary point, because my gradient function, the thing I'm drawing now, is 0. Right? Okay, now in between here, right, what's going on? The gradient function is negative. That's what all of my negative signs mean. Right? And I've got to have, it's got to turn around, lining up with this point of inflection that I've identified. Okay? So in between pi on 2 and 3 pi on 2, I'm doing this. It's negative, it's negative, it's negative. There's my point of inflection, turning point. Right? But it's got to come back up to 0. Right? So it turns around, and there I am. Now what's happening here? What's happening here is kind of the reverse of what's happening here. Can you see this? This is positive, but it's going towards 0. This is positive, but it's going away from 0. I'm trying to describe the gradient here the whole time, right? So I'm going to be above the axis, but I'm moving toward a stationary point. It's going to look like this. Okay, now, I should have brought another color with me, but it ran out. So let me just make it really thick and awful looking as a graph. But that way you can at least tell that it's a different thing. This graph I've just drawn in, I'm suggesting is the derivative of sine. Okay? It matches all of the features that we've just described. Okay? That you're starting off here, you've got a stationary point for the gradient, reflecting this point of inflection, and here, and here. It's positive when I need it to be, negative when I need it to be, positive again, and here are the zeros corresponding to the stationary points on the original graph. Okay? And of course, as we know, this thing will keep copying because it's periodic, just like sine is. Okay? So now you can tell me, because you know very well what this graph is, what does the derivative of sine look like? It looks like cosine. It sure looks like cosine. All right? So let's just see if we can play with that for a little. Because once you have this, you actually get every other trig function and all its derivatives bundled along with it, which is kind of nice, right? They all come from here because they all come from sine. For instance, let's think about cos. If I know what the derivative of sine is, what's the derivative for cos? Well, I want to try and, you guys know, maths is so much about getting problems you don't know in terms of problems you do know, right? And trying to mess around with them that way. Now, this is a trig function. The only other trig function that we know the derivative of is sine. So what can I do to this to twist and turn it so it'll look like sine? What's the definition of cos? We talked about this last lesson, that the co stands for complement, right? So the idea we would usually say is, you know, cos x is equal to sine of, now what are you sticking there? To make the complement, how do you get the complement? Like if I had, say, pi on 3 here, you'd expect pi on 6 here, but what's the relationship between those two numbers? You add them together, you get pi on 2, right? So this is what I should have here, pi on 2 minus x. Are you okay with that? And of course you can flip it around if you wanted to. So I'm going to substitute that in here instead of cos. I like that better because I know how to differentiate sine. At least I think I do, right? Let's see if it works out. How would you go about this? You kind of got two options, don't you? You could use a trig expansion here, couldn't you? You could expand it because you know how to do sine a minus b, right? But you'll end up with a problem. Anyone tell me? You'll end up with another cos, won't you? Which puts you back in the same boat. So you're like, okay, that's not a great way to go. But there's another tool in your differentiating toolbox that you know that you can use to deal with this, right? Which doesn't introduce another cos in. What can we do with this? You could substitute something in here, couldn't you? Another way of saying it is you could use chain rule, couldn't you? This is a function of a function. That inside function is pi on 2 minus x, right? So can we do this? We can do this, can't we? What's the derivative of the inside? If I said the inside function is pi on 2 minus x, what's the derivative of the inside? It's just -1, isn't it? -1. Good. Done the inside. That was hard. See if we can do the outside. Will it be any easier? The outside function is sine. I just suggested, I proposed that the derivative of sine is cos. So what will it turn into? It'll just be cos of, but don't forget, it's the inside function, isn't it? Pi on 2 minus x. You okay with that? But wait a second. Remember I just said we could use this identity, but you can say it around the other way, right? You can just as equally say sine is cos of pi on 2 minus x. Those two angles relate to each other in exactly the same way. They're both complements, right? So therefore here, I can get rid of my cos again. And I get that. Hold on. Stop for a second. I'm suggesting the gradient of sine looks like cosine. But having gone through this is telling us that if that's true, then the gradient of cosine is negative sine. That's confusing, is it? But is it true? Is it true? Well, let's have a look. Let's try and do the same thing we did for sine, but do it very quickly for cosine, because I think we've sort of got the idea, right? from 0 to this stationary point, which is at pi, right? What's the sign of the gradient? What's the sign of the gradient from here to here? It's negative because it's a decreasing function, right? So that's why your gradient is down here, okay? Because it's a decreasing function. I can use the opposite argument and say, well, this part's positive, so it should be doing this. And sure enough, that looks a heck of a lot like a negative sign, okay? So this looks like it works out, okay? There's one more basic trig function that we know. Tan. Okay. Now, someone remind me, what is tan? Like, what is the definition of tan? It's sine over cos. So you're like, oh, gross. Quotient rule, really? Relax. It's not that bad. This is U, and this is V. Okay, help me out. What do I do? So, what is the quotient rule? So, U dash, you told me is cos, right? U dash V, okay? I can do that, right? What's in between? Minus, be careful. So you just told me U dash V, so I suppose we should do V dash U. V dash, what did we just say? Negative sign. What's your signs? Get it? What's your signs? Anyway. V dash U, okay. One more sign on the end. Okay. All over what again? V squared, which in this case is this. Okay, what am I getting? I've got cos squared plus sine squared, which is? Okay. So there you go. There's 3 results. Cos and tan, which of course are built off of sine.